What awaits us today? Today's focus is exciting and trending topic, hydrogen and hydrogen-oriented projects. We have the set of two presentations today that promise to realize groundbreaking development in this field. I am honored to welcome representatives from Linked company and the Institute of Thermomechanics, Czech Academy of Sciences, together with UJV Řeš, who will share their R&D projects. Now, I would like to invite Mr. Havlíček from Export Insurance and Guarantee Company to take the floor.
Thank you, Martin. Thank you all for joining us to this great session. I also welcome you here. My name is David Havlíček. I work for IGAP, as Martin said. IGAP is a Czech insurance company, state-owned, and our goal is promote export. And together, Technology Agency and IGAP cooperate in early decade to really find some potential projects which was supported by state, especially Technology Agency, because Technology Agency gives R&D grants, and following by credit insurance by IGAP, and help them get to the market, get to the global market. So that's one of the way how to do it, connect the great Czech ideas with potential customers or other stakeholders, and promote their ideas to the world. So we are planning to have this session about 1 hour. Each presentation will take 15 minutes, and after that, after each presentation, you will have a floor for your potential questions, and then we follow with the second presentation. So that's all from me, and now floor is for Linked, company Linked, and Vladimír Matolín, who will introduce the presentation. Floor is yours.
Hello, thank you very much for this invitation here. I am really happy that I am able to show what Linked company is doing. Linked is a company which has been founded in 2016. It means 7 years, 8 years ago. Basically, our goal from beginning was connected to development of new electrocatalysts for fuel cell and electrolyzers. This is also the reason why the name is Linked, which means same catalyst. This is not animal. However, from the beginning, we understood that it was too early to go to the market with new catalysts, cheaper catalysts with lower content of precious metals. And finally, the company developed two main branches of production. The most important for the moment, because it's more developed, is production of fuel cell test station and electrolyzer test stations. And 2 years ago, we started to develop our own water electrolyzers. So that's Linked. So we have these two main lines where we are working and we are developing. Okay, so now maybe I don't know if everybody understand what is the reason of development of water electrolyzers. Hydrogen, for the moment, is the main pillar of decarbonization. There are two motivations to develop hydrogen, which is called renewable hydrogen made from a clean energy like electricity, like basically photovoltaics and wind turbines, maybe. And the reason is, so one thing is decarbonization, which is pushed by Green Deal, and the other reason is more recent and maybe more sad, is that hydrogen seems to be one of the main elements which will help to replace natural gas, which due to the problem of war in Ukraine. There are several techniques for water electrolysis. Probably the most developed is PEM water electrolysis.
Martin, maybe you will share the presentation with us.
No, sorry, I didn't do that. Okay. It's okay?
Yeah, now see it. Thank you.
Okay, so I'm very sorry that you didn't tell me that before. Okay, so it's fine now?
Yeah, now it's
okay,
fine.
Perfect. And PEM water electrolysis is a state-of-the-art technology, but of course, as new technology, it suffers from different drawbacks. And even one, probably the most important, which is causing a problem of large development, is high operational cost and needs the high capital cost. This is due to use of precious metals and many special elements. And but the main reason of that is small repeatability of component production, and it seems that the way to cheaper production of clean hydrogen is to go to scaling of production and to go to a large scale production. One possibility how to do that is this is what where the LINKET is addressing this issue, is the development of modular electrolyzers, which means, and I will show that later, it means that we are developing the system where we are repeating the small modules and building like a puzzle the bigger system for hydrogen production. Okay, so very shortly how PEM water electrolyzer works. PEM means proton exchange membrane. In the central part, we have a membrane which is proton conductive, which is sandwiched between two layers of catalysts on the water side, where because water is dissolved and forming hydrogen, we have iridium catalyst, and on the other side we have platinum catalyst. Water is split to electrons and protons. Protons go through the membrane, and on the cathode side is forming hydrogen. So it works in this way. This is some kind of the system which can be considered a reversible fuel cell. There are several reasons why this is the most popular. One is that it's can operate or can be used for mobility because it's relatively sorry, they can be used for confusing with fuel cell, which can be used for system where we don't have stable source of energy, typically photovoltaics. Well, now let's go to LINKET production. The system for production hydrogen is, which is also called water electrolyzer, but in fact we can call it as a hydrogen generator. Contain the electrolyzer stack. You can see that the family of water electrolyzer stacks produced by LINKET of different sizes, and this stacks can be, it's composed of cells. Cells are stacked in a serial way, and in this type of electrolyzer, we can go from 1 to 5 kilowatt, and hydrogen can be produced with relatively high pressure. We are wanting 25 bar, and the system typically is designed for integration in other generations. So we are selling the electrolyzer to integrators, but we are developing, as I will show later, also our own system. The specialty of our electrolyzer can be seen here because this is very compact system. We integrated heat exchanger in the electrolyzer because anodic loop where the water is circulating should be cooled. And in that case, so this is the electrolyzer, and this is the heat exchanger system, and making the system so compact we are making a lot of economy concerning the necessary space. And well, so the linked effort is based on two pillars. The first one is development of compact electrolyzer. Our system, or what we are looking for, is durability. It means all internal system I made from titanium. It is metallic system, of course, and we are coating these parts inside the plates and other components and flow fields. We are coating this anti-corrosive layer for limiting the oxidation of titanium, and due to that, the electrolyzers has very nice durability. As I said, so we have also we can show this integrated heat exchanger. This example here shows the system of 3 kilowatt electrolyzer, 2 kilowatt and 1 kilowatt, this heat exchanger. Okay, so what about the performance? Example of 1 kilowatt electrolyzer is producing 5.4 normal meter cube, means pressure of hydrogen per day at 25 bar. I said that our goal is to have the system with high durability. We can see here these two lines showing the difference of IV curves after 1 year of utilization, and after 1 year of utilization, we produced only 2.7% of efficiency. So this is the technical parameter, but I think that the most interesting is this 270 liters per hour, or this value which I have shown. On the other side of our portfolio is this 5 kilowatt electrolyzer, and in that case we can produce 25,000 liters, in this 25 normal meter cube of hydrogen per day and 25 bar. So this and stack voltage is typically the best, or the, how to say, the current which can be called as a nominal current is 50 amps. At 50 amps, we have a voltage at one cell which is 1.99 volts, which shows efficiency about 80% for the stack. Second pillar is integration of electrolyzers to modules. We are developing 3 to 5 electrolyzer modules, which has high level of autonomy because each module is controlled by embedded computer inside. And as again, I am repeating that we have relatively small size of modules due to the integration of heat exchanger into the stack. So this is some kind of diagram showing how the system works. And this is the module, and the module can be stacked as you can see here. And the ground module is a common one where we have the system of deionized water and the chiller. Okay. For this modules, it means the system generating hydrogen, we need more components, not only a module with water loop and the stack. Hydrogen which is produced is wet, because of penetration of water or diffusion of water through the membrane from anode to cathode. So the system should be equipped with water separator system here and electrolyzer and hydrogen dryer. This is a system which we developed. We are also offering that in the market. The system is composed of two columns of absorption using molecular sieves, and the system can work continuously because one column is working. It means it's absorbing humidity from hydrogen, and other is regenerated. Because when the system starts to be saturated, we can measure that with a hydrogen sensor, and the system switch automatically, and we start to use this one, and the other columns start to be heated for the regeneration. We developed also other components like ion trap, because for PEM electrolyzers, it's very important to have high quality water with very low conductivity, which can be get by introducing ion trap into the anode water loop. So this is also something what we are producing and offering to our integrators. And the system where we, because probably you know that the big electrolyzer which are used for massive production of hydrogen has several megawatts. We don't produce that one. On the other hand, we have integrators who would like to make maybe half megawatt system by stacking the modules. On the other hand, this small electrolyzer can be used for distributed production at home, at small companies with solar panel on the roofs. And one project where we are involved with home backup power, where we can produce, or the system producing electricity, and the electricity can be in summer used also for producing hydrogen storage for to be used in winter, and winter is a fuel cell, so we can produce the electricity back. Or it's also possible to burn it, this would be even cheaper. Well, so this is we are also focusing an effort to educational system, because the problem is that hydrogen technology development suffer lack of specialists, and we have this single cell electrolyzer with a small one-chip computer, where the students can measure different parameters and plots of depending on the temperature, on electric power and electric current. This is transparent, so you can see also the bulbs of oxygen are produced on the anode system.
I'm sorry, Mr. Matolin, you have only a few minutes.
Okay, I think that it's fine. The ongoing project is to develop the bigger electrolyzer, 50 kilowatt. Here, we are already testing the short stack, and by stacking 50 cells, so we can go up to 250 normal cube meter of hydrogen per day, which is suitable to modular system where we can go up to 1 megawatt. Maybe one of the last information for this electrolyzer business, we are developing also water electrolyzer test stations. This is one which is already commercialized. This year we sold first 7 systems to our customers, which so this system is necessary, is used by people who are developing electrolyzers of component of electrolyzers. Okay, that's all. I would like to thank you for attention, and I will be happy to answer your question if you have some. Thank you very much.
Okay. Thank you very much, Mr. Matolin, for your great presentation. Now it's floors for questions. You can, I'm sure, write questions to the chat or just raise your hand or to just turn on your camera and we will see that you want to ask. So you have many ways how to ask. Maybe before everyone, I will ask you, you said that there is a demand for hydrogen rising. Is it in, let's say, all parts of the world, or it's mainly, we can say Europe, maybe US, due to also, let's say, Green Deal politics and so on? Yeah, Mr. Matolin, if you can said if you see the growing demand for hydrogen also from, let's say, other parts of the world.
Yes, so we can see that because this year the number of electrolyzers selling is growing exponentially. Means that during last 3 months, or 4 months, we sold already maybe more than 10 electrolyzers. Now we have customers in the US. We have 2 customers in US and California. We have customers in Canada and Netherlands, and also China, India, so in different countries.
Mm-hmm. Okay, thank you. Now, floor for your questions. We don't see any in the chat, so if you want, just ask. Yeah, Jana Tucháčková, you can ask. Hello. We don't hear you. Yeah.
Yeah, sorry. I'd like to ask because you have quite special technologies, and what is the competition between your company and other companies, not only in Czech Republic, but in other countries like around Europe or in general around the world?
This is a very good question, and we also would like to know the answer, because it's not easy to have this type of data. All our experience is coming from customers. For example, we discussed this one company in the US, we proposed the electrolyzer. They told us it's okay, it's nice, but it's quite expensive. We were sorry, so the price is as it is. And 2 months after, so they returned back, they told me, okay, but we didn't find any other supplier. So it seems that in this field of small or medium-sized electrolyzer, there is very small production, not in Czech Republic, definitely not, and in other countries, because company now are, or big companies are focusing maybe to big electrolyzers for megawatt and more. So we know that there are some electrolyzers produced in China, but what we can compare, if we compare it to electrolyzers we have seen, this is in our case very compact size, which is important for developing the modular system. But I am not able really to answer because we are not able to map the situation. And of course, if we are asking as a company producing electrolyzer the price, so we didn't get it. But well, I think that it's quite limited, definitely.
Okay, thank you. Thank you for the question and for the answer. If anyone else has questions, don't hesitate, just ask. It's a great opportunity. Well, Doesn't seem that there are any more questions. So thank you again, Mr. Matulin, for your presentation and your answers. And now we can switch to the second presentation for Mr. Němec and Mr. Klucký about their project. And floor is yours, Mr. Němec. Okay, perfect. We see the presentation.
Good morning, everybody. I hope you can hear me and you see my presentation. I would like to talk today about making catalyst nanomaterials and making layers of these catalyst materials. And these layers could be used for different hydrogen technologies, as I would like to show you. I'm coming from the Institute of Thermomechanics of the Czech Academy of Sciences, and there is another colleague of mine, Miroslav Klucký, from the UJV Řeš, which is a company that cooperates with us on this technology. I will pass over to him in a few minutes to introduce himself. At first, maybe a few words about our institute. We are a public research institution, a part of the Czech Academy of Sciences, and historically we have been involved in research and the development of steam turbines for power cycles. The institute was looking at erosion of the turbine blades, for example, studying how water is condensing, how the wet steam is flowing in the turbine. And there was also some theoretical development of erosion models and nucleation models. So with this knowledge at hand, we started to look at condensation of metallic vapors back in 2015, meaning this condensation process can create nanoparticles, metallic nanoparticles, and these could be used as electrocatalyst nanomaterials for various electrochemical processes. So in 2019, we teamed up with UJV Řeš. We started cooperation on these condensation, evaporation processes, and asked them whether they could help us with scaling up the technology that we had so far. So maybe now Mr. Klucký, he could introduce the UJV company.
Hello, everybody. So about UJV Řeš. Currently, UJV provides a wide range of expertise and services to operators of nuclear power plants in Czech Republic and abroad. UJV ensures the development of the use of ionizing radiation and irradiation service for basic and applied research, healthcare, and industry. UJV ensures the production of radiopharmaceuticals. In addition, the institute also operates in non-nuclear areas. For example, in field of classics energy, chemical industry, and environmental protection, and hydrogen technologies.
Okay, so what we are focusing at, it's it's hydrogen technologies in general. You can see a hydrogen car here being filled up at UJV at their filling station. And the hydrogen car has a fuel cell stack instead of a internal combustion engine as a usual car that we know. The fuel cell stack is an electrochemical device converting chemical energy into electricity. And at the heart of the fuel cell stack, we have the MEA, which is the membrane electrode assembly. And that's the main component where actually the chemical reactions are happening. And this is the main component in terms of efficiency of the whole fuel cell stack. Optimizing the MEA structure, performance is a key to have an efficiently operating fuel cell. So if you look at the cost of the fuel cell, the MEA and the electrodes on the MEA in particular, they represent a considerable part of the total cost of the fuel cell. And this graph that just shows you if the fuel cell would be manufactured in high volumes, then the electrode is the main component, which still costs something like 51% of the whole cost of the fuel cell stack. What we would like to present is an MEA production process that is competitive to the standard process which is being used at the moment. On the left, you can see how the MEA is produced nowadays by commercial companies. You typically need 3 steps. And the first step would be the synthesis of the catalyst material. The second step is coating of this catalyst material onto either the membrane or the gas diffusion layer. And having this, you can produce in step 3 the MEA by various processes, hot pressing or different ways of laminating the layers onto each other. In our case, we are able to merge step 1 and step 2 in one device. That device would first produce the catalyst nanoparticles and directly do the deposition on a gas diffusion layer. You see this laboratory device in this picture, and there is actually one chamber, the round in the top of the image, where the nanoparticle synthesis is being performed, and in the lower part there is another chamber used for deposition of the catalytic layers. The technique, the method is based on spark ablation, which basically uses
Sorry, Mr. Nimetz, probably we are almost frozen.
Some technical problems.
Maybe if Mr. Klutsky hears us.
Okay, I will continue. Its process is the current gas go into the chamber and between 2 electrodes. between the electrodes is this charge, which can evaporate the electrodes in the chamber, and evaporated platinum is condensate into the nanoparticles. How you can see in the picture, the nanoparticles can be deposited on the diffusion layer and make the gas diffusion electrodes. Here is the pictures of electron microscopy. When you see how the nanoparticles is coagulate or its size, it's around to 5 nanometers. What is benefits about our device? The main is the high purity, where the purity of the nanoparticles depends on purity of electrodes with low weights. The process is very simple, and you need no solvent, like in the different type of use of nanoparticles. And you can use also 2 types of electrodes, for example, platinum and iridium, and you can make the mix of catalyst, like platinum iridium mix. Where it's possible to implement our nanoparticles or our device? It's in the hydrogen technologies, in the PEM system, PEM electrolyzers, and electrochemical compressors. The platinum nanoparticles also used in gas sensor, supercapacitor, and in the research and development. For example, synthetism of chemical compounds, like general catalyst. Here is the picture of the mass. Where you see the right picture is electron microscopy. You can see that we can have the different thickness of catalytic layer. One layer is anode and is thin than the layer in the cathode. In the left picture, you can see the where is membrane and hot pressing the diffusion layer with catalyst. Here you can see the properties of our catalyst, of our mass. There was measured at the Institute of Thermomechanics, where is the a lot of measurements with different pressure and with different output current. And okay, what is our target? Our target is have the better properties than commercial mass in the current market. And now we are developing better how to say it, structure, sorry, better structure of the deposit nanoparticles for increasing of output power of mass. What is the near-term goals? For us, it's modular design. For market, it's like spark chamber plus deposition chamber plus pulse power unit. Next is optimization and manufacture of spark chambers and deposition chamber. Optimization and manufacture of high voltage pulse power. New control software for process control, monitoring, and automatization. And technical and safety standards compliance. For long-term vision, we would take our products for fuel cells and electrolyzers and make cooperation for the best product of the market and make the scale up of larger active area mass. Now it's maximum for us 100 centimeter square, and scale up to product of nanoparticles to 1 kilogram per day. Davis can be operated not only with one discharge chamber, but with several discharge chambers at the same time. The expansion of the equipment from 1 chamber to 4 chambers has been tested for a long time at UGV. It is also possible to increase the area for deposition gas diffusion electrode. Currently, the application is tested on the area of 100 centimeters. The increasing in deposition area is associated with the possibility of connecting several discharge chambers to one deposition cell and speeding up the deposition of large areas. It's also possible to increase the frequency of electric discharge and thereby speed up the process of evaporation of platinum from the electrodes. Here in the pictures, you can see a semi-operation Davis working with 4 discharge chambers. The Davis was tested for more than 1,000 working hours, during which was optimized. A total of 35 grams nanocatalyst was produced. As I already said, increasing the output of one cell is possible using higher discharge frequencies. Unfortunately, a higher frequency increases the probability that part of the platinum electrode will not be evaporated but melted. Melted platinum electrode create platinum residues that must be removed. Creating a process for such purification would be greatly assist in the speeding up production by this method. How you can get involved? So it's pre-order of our laboratory Davis to produce own nanomaterials or nanocatalysts. That's our GDEs or mass for hydrogen fuel cell or investment. Also, it's possible involved in research and development. So expansion and simplification and automation of products process. Now we have the produce line with 4 chambers. Increasing of safety of operation and establish technique to tackle scale-up challenges. Thank you for your attention.
Thank you, Mr. Klutsky and Mr. Němec, but I'm not sure if Mr. Němec is still with us. Thank you for the presentation. I have 2 questions for you. First, if I understand it correctly, your results can lower the price of fuel cells. So in, let's say, industry scale, how much you can save on the fuel cells in percentage points? So this is first question. Second, if these fuel cells can be used, let's say, not only in cars, but for example, I don't know, in trains, because in the automotive, hydrogen cars and electric cars are quite of competing of the market. But for example, in train industry, what I heard, they are complement that in the future there will be hydrogen trains on the long distances and electric trains to the short distances, and can really complement each other. So if these fuel cells are, let's say, usable also for other fields. So these are 2 questions on you, probably, Mr. Klutsky.
Okay, I will start with second question. So it's not about just automotive. It can be used, for example, in stationary, like for power unit in the hospital. When the electricity is blackouted, you can use the hydrogen technologies with our catalyst for the generation of electricity. And what was the first question?
The question was how much your technology can save from the price of fuel cells on the market.
Maybe I can try and help with answering that question, Mr. Klutsky, or unless you feel comfortable answering it.
But question about the save money, it's a question for Tomáš Němec, but it's freezing.
Yeah. Sure. Maybe I can just introduce myself. I'm Radka Bartosová. I work at the Czech Academy of Sciences at the Technology Transfer Office, and we are supporting Tomáš Němec and the Institute of Thermomechanics in commercializing the technology. So, and it was a very good question you asked, sir, from Thatcher, and it's a question we are asking ourselves as well. We have dedicated an expert on this question right now, and we are together. We are finding and putting together an answer to this. So I hope, like in a month, we will be able to give not an accurate estimate, because that's a very difficult question, but we will get closer and a better estimate of that answer. At the moment, we think that it could be cheaper, but we need more information to support that claim. So we are working on it, and I can see that Professor Mettelin is raising his hand, so maybe he would like to comment that.
Yeah,
sorry,
Mr. Mettelin probably has another difficult question, but thank you for that. I completely get it. Yeah, Mr. Mettelin.
I will continue this discussion. Well, so the question is connected to a very important parameter, which is platinum loading per unit of the surface. So do you know that or not? How much platinum for the period per 1 square centimeter? Typically, this is a value which is given for comparing the content of platinum group metals on the membrane.
Maybe I can answer that question if you hear me.
Yeah.
So we can deposit various platinum loadings with this device. It's quite easy to change it. What we aimed at during our tests was 0.2 milligram per square centimeter of platinum at the cathode side. And those results that you saw in our presentations were measured with an MEA having 0.2 milligrams per square centimeter.
This is certainly a low value.
So that means that it can be cheaper.
To my understanding, the typical standard nowadays is 0.4 milligrams, and really high-end MEAs, for example, which are used in the Toyota Mirai car, they have 0.25 milligrams of platinum at the cathode.
Yes, so it's the problem of loading or relatively high loading in commercial system is that high loading is used for increasing the durability because higher amount of platinum ensure that the catalyst, so the performance is bigger for longer time. So I think that probably, as I understand, this is a relatively new system. So the complete answer depends also on durability of the system after maybe some stress tests or something like that. But then also the performance of which you have shown for 0.2 on the cathode, which is very the problem of kinetics of the reactions, looks promising.
Yeah.
Okay. Thank you for the follow-up from Mr. Matolin. Mr. Němec mentioned Toyota Mirai. Maybe one fun fact that two of our ministers in Czech Republic is driving Toyota Mirai. So there is really in use even on this level. Okay, there is sure space also for another question if you have. Just type it, or as before, just turn on your camera and we will see that you want to ask.
We have another about 6 minutes, so don't hesitate to use the time for questions and answers.
Yeah, Mr. Matolin.
I'm sorry, but there are no other questions. So this is field which is very interesting. Can you give us an estimation of deposit speed? It means how fast the process is for coating the membrane.
This laboratory scale device that we have at the moment, we can go up to 50 milligrams per hour of production rate. Now it also depends on the quality of the nanopowder that we want to produce. Actually, higher quality means that we need to go lower with the production rate. In that case, we will get smaller nanoparticles, we will get higher porosity of the nanomaterial, but in that case, we are at around 10 milligrams per hour, the production rate.
Yeah, so I think that it need a big effort on this side because industrially, so the typically used technique is slot die printing, and the speed is in seconds to deposit to 1 MEA.
Exactly. So in the industrial scale, we would need to run something like 1,000 of our units in parallel to get some reasonable production rate. But at the moment, we are really aiming at a laboratory device that could help the scientists, that could help the companies to develop the MEAs, to develop the catalyst layers. And in that case, a few square centimeters active area is just fine for your testing. And this will take a few minutes to deposit.
Okay.
Okay, thank you very much for the question and the answer. just be sure that after this presentation, we will send you this presentation on your emails, which were registered at first place, so you can get the contacts on the presenters and can ask them afterwards. So don't hesitate, contact them even after this session. One last chance to ask. If no one has a question, so thank you very much from our side. Thank you for joining us. It was a pleasure, and presentations were beautiful, and thank you for questions and answers. I think hydrogen will be a more and more frequent theme on the not only R&D but also economically and politically fields, and we are looking forward for the hydrogen future. Martin, if you want to add up something.
That's all from today's workshop, I think. I would like to thank to all of you for your participation and engagement in today's workshop. I wish Linked Company and Institute of Thermomechanics and UJB Řeš great success with their projects. Thank you for being a part of this workshop, and I wish you all a nice rest of the day.
Thank you all.